Hi, I'm Anthony.
I'm Edwin, and this is MetaHDR, Model-Agnostic Meta-Learning for HDR Image Reconstruction. As we know, there exists a nonlinear mapping between scene radiance and pixel values that is dependent on scene, camera, processing, etc. While existing deep learning models learn a single nonlinear mapping across all scenes in a dataset, we propose a meta-learning framework that can adapt to any nonlinear mapping by producing a set of meta-parameters which capture the common structure between LDR to HDR conversion tasks.
Therefore, the problem we are trying to tackle is as follows. Given n LDR images, produce one HDR image. As an example, here's a set of three exposures of the same scene taken from the dataset we used, as well as the true HDR image. The dataset we used had 450 scenes, where each scene had three LDR images and one HDR image. To get an HDR image, Devivek et al. Fused together a series of images captured at different exposures using exposure weights. However, current approaches use deep CNNs to attempt to model a single nonlinear mapping to predict the HDR image.
For our approach, we employ the meta-learning framework known as MAML around a UNet architecture. The UNet performs the image reconstruction, while MAML enforces model weights that are quickly adaptable. The weights of the meta-learning model are denoted by theta and encapsulate a general solution that is close to many nonlinear mappings, but specific to none. We treat each set of 3 LDR and 1 HDR images of the same scene as one single task. At meta-train time, we sample a batch of tasks and perform a train step on each task as follows. First, during task-specific training, we compute task-specific phi I by adapting the metaparameter weights theta using the LDR images of each task. Next, during task-specific testing, we use the adapted phi I to generate a predicted HDR image for a held-out LDR image of the same scene. Finally, we compute a loss for this task, accumulate over batches, and adjust metaparameters theta accordingly. Over all meta iterations, this algorithm will produce metaparameters that can quickly adapt given multiple scene exposures.
Here, we see results in both single-shot reconstruction as well as adaptation, where we use multiple LDR images at meta-test time. I want to highlight a few things. First off, the results from a visual standpoint are pretty impressive. For example, the LDR test image for the cabin was taken with a long exposure. However, our model was able to fill in saturated pixels correctly. Additionally, we see single-shot reconstruction is possible. However, adaptation improves model performance by looking at both the SSIM and PSNR values.
Quantitative SSIM and PSNR metrics over all tasks/images in the held-out meta-test set demonstrate our model's ability to perform well in the single-shot and few-shot settings. Since users won't have access to ground truth HDR images for adaptation at meta-test time, these need to be simulated with existing deep CNN approaches. During meta-training, we use these simulated HDR images as task-specific labels. Compared to using the ground truth HDR images for task-specific labels, the simulated method actually improves quantitative performance metrics as seen in table columns 3 and 5. Note that state-of-the-art deep learning approaches achieve quantitative results around 0.7 for SSIM and 18 dB for PSNR on the same set of test images. In conclusion, there are many ways to construct HDR images from LDR inputs. Using existing heuristic-driven methods require many images across a wide range of exposures. Using existing data-driven methods assume one nonlinear mapping exists across all scenes. Our novel approach to data-driven HDR image reconstruction is capable of generating any nonlinear mapping specific to the scene in question. It is able to perform single-shot and few-shot HDR image reconstruction using conventional imaging equipment.
However, there are challenges. For example, color saturation was hard to maintain between input and output. Additionally, as we have talked about, labels need to be simulated at meta-test time for model adaptation to work. In the future, we hope to incorporate loss functions that prioritize saturated pixels during reconstruction, and we'd like to train with more exposures per scene and use more scenes to create a better model overall. Thank you for listening.